Good evening. Welcome back to AP Stats Notes Online. We want to talk a little bit about these sampling distributions, and we started collecting and creating some of our own sampling distributions, both with our poker chip activity and the German tank activity that we started working on. I want to wrap up the last question from the previous set of notes, only because I think that it's really, really important, and I know I keep saying this, but it is, and we need to make sure that, again, that we understand the difference between the distribution of a population, right? The distribution of a population simply shows what the population looks like, okay? Whether it be a bar graph or a box plot or a dot plot or whatever, depending on the variable that we're measuring, whatever the parameter is, the distribution of population shows what the population looks like in terms of the individuals. What do all of the individuals look like, right? The distribution of the sample is kind of the same thing as the population distribution, only it's for a sample of the population, right? This shows what a sample looks like, or what the individuals in a sample looks like, right? And it should probably be the same type of distribution as your population distribution, right? Again, depending on what type of variable the statistic is. If it's a categorical or quantitative variable, and that will dictate what type of distribution we use. Now, the distribution of a sample statistic, the sampling distribution of a sample statistic, and the wording of this is very important too. You don't want to call this anything other than a sampling distribution. It's the distribution of all possible samples, okay? But it's going to show what all possible samples look like. Right? And so if we're going to take a sample of, say, 10 of something, in order to plot that into a distribution, we have to have some sort of statistic measured on it. Right? So we'll take a sample of 10 and calculate the mean, and the mean becomes what we put into our sampling distribution, right? So this is going to include some value of the samples, not the individuals, but it shows the samples, and it's whatever statistic that we're trying to estimate or trying to calculate, right? And it can be anything. So this shows individuals, this shows individuals, this shows samples, and what happens when we start sampling, okay? Ideally, all the samples, but that's not really ever going to happen. So most of the time, we're going to look at an approximate sampling distribution, okay? So those are your differences, and this might be a bar graph, which means that this might be a bar graph, which means, but the sampling distribution, since we're doing the actual numerical calculation in terms of a statistic, a mean, a proportion, a Q1, a Q3, or whatever the calculation is, then this distribution will be any distribution you want involving a quantitative variable, whether it's a dot plot or a box plot or a histogram or whatever. If this is a bar graph because the variable is categorical, this will still turn into a dot plot or a box plot or a histogram, because it will turn into a quantitative measure that makes sense to find the mean of, okay? So I want to make sure that we wrap that up. Now, that being said, the German tank activity gets us thinking a little bit about when we take a sample and do a calculation on it. The idea is that statistic that we get from this sample should give us a good idea of the entire population, right? What proportion of people think President Obama is doing a good job, his approval rating, right? When we take a sample and calculate the p hat of that, which is the proportion of people that think he's doing a good job, then that hopefully tells us what the population is thinking. But only if the measure, the statistic that we're using, is a good estimator of the population parameter. And that gets us into, all right, when we have a sampling distribution, and so ideally we don't take one sample, we take a bunch, and plot those proportions into a sampling distribution, then we want to take a look at that distribution and be able to describe it and know what it is that we're looking for in order for our statistic to be a good estimate of the parameter. Now, what I mean by that is we talked about this already in terms of sampling variability from the last notes, right? Whatever it is that you're measuring, when you take 10 samples, and again, if I ask one sample of people, do you think President Obama is doing a good job, then that proportion, that p hat, probably will not be the same, could be, but probably will not be the same for the next sample. So those approval ratings will vary. They'll be different. Some of them will be exactly what the population thinks of Obama's approval rating. Some of them will not. And so what we do is we create some sampling distribution, right? And if it's a collection of p hats, that's what we're talking about now, right? I mean, it might look something like this. The question is, what do we want the sampling distribution to look like? We understand there's going to be some variability, but we still want our statistic to be as accurate as possible. And so how much variability, what is the ideal situation for a sampling distribution? If we plot the sampling distribution, what's the ideal shape, center, and spread of this thing so that we have a good idea of the parameter? Okay? And so that's where these questions come in when we describe our sampling distributions. Okay, first is, what is an unbiased estimator is the first question. Well, when we start talking about bias, then we're talking about the accuracy, right? This involves the accuracy of our statistic. How accurate is it? How often does that statistic fall on the actual value of the parameter? Okay? And so to be an unbiased estimator, these dots need to be centered on the actual population parameter. So say the true P, the true proportion of President Obama, of the people that think President Obama is doing a good job, might be there. Then if our statistic, if our P hat from all of our samples is accurate, then the sampling distribution will be centered around this actual P, right? And so that's what we mean by an unbiased estimator. The center, and again, ideally, we're talking about the mean, right? Because what your questions here won't talk to you about is shape. Now, again, our favorite shape in statistics is normal. With a normal distribution, then we're getting into a symmetric distribution that's single peaked. I don't want two peaks, because then I'll have two possible values that might represent the parameter, and that's not what I want. We want one peak, right? I want most of my data to fall in one area, because then it seems to be a bit more accurate. There's one value. Obviously, the parameter has one value, and so we'd like for our sampling distribution to be centered around one value. So no two peaks. And then if it's symmetric, then we don't have anything pulling our statistics one way or the other. So we'd like for it to be symmetric and single peaked, and normal gets us there. Bell curve would be nice, would be great. So if we're going to want a single peak symmetric sampling distribution, then it makes enough sense to talk about the mean. So if a statistic, and this is for a statistic, if the mean of the sampling distribution of a statistic is equal to the population parameter, and I think population parameter becomes redundant, is equal to the parameter, then we call that statistic an unbiased estimator. There's no bias. How accurate, right? There's nothing that is moving the statistic value away from the parameter, okay? And we're talking about accuracy, all right? Now, some statistics we know to be unbiased estimators already, and some are not. And so if we were to take a bunch of samples from a population and calculate the mean, whatever mean it is that we want to know from the population, and plot those, then the mean is an unbiased estimator. In the sampling distribution of a mean, the center of that sampling distribution would be equal to or really, really close to the population parameter, the parameter that we're trying to estimate, okay? So unbiased or bias talks about accuracy. If it's unbiased, if this is an unbiased estimator, that means that our statistic is pretty accurately, is very accurate and takes on the value of the parameter very often, okay, or really close to it. Obviously, if it's a biased estimator, then it won't. It'll consistently be away from the parameter, right? So I mentioned means, proportions we know to be unbiased estimators. There are other things that we know to be unbiased estimators. As a matter of fact, on page 423 in your book, there's a Think About It section that walks you through why, when we do a standard deviation calculation for a sample, why we divide by n minus 1. I tried to squirrel my way around it before because we weren't ready to talk about why. But this section in page 423, and I really encourage you to look at that, shows you that when you calculate the standard deviation by dividing by n versus dividing by n minus 1 for a sample, the dividing by n minus 1 turns out to be an unbiased estimator where dividing by n is not, okay? So that's why the formula ends up dividing by n minus 1. It's a lot more accurate measure of a statistic as far as estimating the possible population standard deviation. Okay, but read that section, it's pretty interesting. Okay, that's what we mean by bias or being an unbiased estimator. It means the center of the sampling distribution is equal to or incredibly close to the parameter. Now, there is going to be some variability. So we want the shape to be symmetric and single peaked, so normal, hopefully. We want the center of the sampling distribution to be equal to the parameter, right? And there is going to be some variability, and obviously we want low variability. We want the spread of the sampling distribution to be really, really small. We're consistently getting the value of that parameter. That would be ideal. So what is the variability of a statistic? It's described by the spread, right? So what we mean is, how big is the spread of the sampling distribution, right? Is it really, really big? I mean, if the center of our sampling distribution is equal to the parameter, that's great. But if the spread is so large that our samples are likely to give us, any range of values and just as often as any other value, then it's not very precise, and so maybe not a very good statistic to use either. So we're talking about the spread of sampling distribution. How can you reduce the variability of a statistic? Well, how can you be more precise? What would you need to be more precise? And obviously, more information is always better, right? So larger sample sizes give us more information. Larger sample sizes will reduce variability. Okay? Now, bias is introduced in a lot of different ways, right? We talk about bias in chapter 4, right? If we sample incorrectly, if we randomly assign, or not randomly assign, if we assign subjects incorrectly, then it introduces bias. In our sample surveys, the way we ask our questions, the way we approach the survey itself, there can be some bias there. And so those things would introduce a situation where our statistic becomes less accurate. Sampling badly is sort of a way we get some bias. Now, you can sample correctly and still get some bias just in terms of how the statistic is calculated. So I don't want to suggest that sampling incorrectly or having bias in your study is the only way that your statistic becomes a biased estimator instead of an unbiased estimator. It can happen even by doing everything correctly. Okay? But with variability, if we want less variability, then that's simple. We just take a larger sample size. Okay? Now, it's not that simple. There are trade-offs for larger sample sizes. Larger sample sizes might include with it a larger cost, a larger time drain, as well as a little bit more difficulty in carrying out that sample because there are too many individuals in the sample that you want. So there are some trade-offs, but if you want less spread in your sampling distribution, we want larger sample sizes because it gives us more information. Larger sample sizes will not improve the bias. In other words, a larger sample size will not make a statistic an unbiased estimator. If you sample more people but do it poorly, then you're still going to have bias in your statistics. So it doesn't fix bias, but it does fix variability taking a larger sample size, right? The last question, what effect does the size of the population have on the variability of a statistic? And interestingly enough, none, right? If I want to know the president's approval rating, then the population obviously is the United States. But if that if the population was bigger or smaller from year to year for whatever reason, this is a terrible example, but the size of the population won't matter as long as the population is larger than, and we talked about this last semester with our probability stuff, is larger than 10 times the sample size. Right? And this had to do with sampling without replacement. It does, when we pull something or someone out of the population, it does change the probability makeup of the rest of the population, but just not enough and to really matter in our calculations until we get to a sample that is bigger than 10% of the population. So the size of the population doesn't have any effect on the variability of a statistic as long as the population is larger than 10 times the sample, right? There's that 10% rule or whatever. Okay? So the point here is when we decide on some statistic, and it could be whatever we've talked about so far, mean, median, Q1, Q3, standard deviation, IQR, minimum, maximum, any of that stuff. Or some crazy calculation combination of those, like you were trying to do with the German tank activity. 2 times standard deviation and add that to the mean. Half the IQR, add that to Q3. Whatever it is that you want to do to combine, that's still a statistic. It's still a calculation that we can plot out into a sampling distribution and see what happens. Look at the shape, center, and spread. Is the shape something that we can work with? Is it single peaked and symmetric so it makes a lot of our calculations a little bit more accurate in terms of not being affected by large values? Is the center of our sampling distribution equal to or close to the parameter? And then lastly, is there less variability? Is there less spread, right? And so I'll show you this thing in the book. There's a picture in the book that does a really good job of sort of explaining what we're looking for as well. If you can think of the parameter as a bullseye we're trying to hit. So whether we know the parameter or not, and right now we're working under the assumption that we know the parameter, then we're trying to hit that target, right? That's the bullseye of a target. We're trying to hit the bullseye of this target. The difference between bias and variability, okay? Well, bias, again, is accuracy. So we want our dots, we want our shots to these bullseyes to hit hit the bullseye on average, right? There's an average bullseye, right? So like this guy has it has low bias, because if we average the distance from the bullseye for those shots, then it would put us pretty close to the bullseye, right? On average, we're hitting the bullseye. Same thing down here, right? On average, we're hitting the bullseye. That's your bias. So unbiased estimator would be what these two shots are showing you. Take that versus variability. Variability is how often are we away from the bullseye, right? Not how often away are the bullseye, but in other words, how spread out are our shots, right? So this guy has very low variability. The spread is small because all of our shots are close together. High bias because we're nowhere near the bullseye, right? But low variability. All our shots are together. How spread out are your shots? Not very spread out. That's what we want. We want low variability, but we'd rather have low bias or no bias. So this isn't necessarily what we want. This shows low bias because we're centered around the bullseye, but high variability, right? The shots are spread out. So we could end up anywhere, but on average, we'll be at the bullseye. Down here shows high bias. Why bias? Because we're away from the bullseye. It also shows high variability because the shots are spread out. Definitely not anything that we want. This guy right here is our ideal situation, right? There's no bias. We're centered at the bullseye, and there's low variability. All the shots are really close together there, okay? That's what we're talking about with bias and variability, okay? And again, shape, we want a shape that makes our calculations make sense. So that's how we want to describe our sampling distributions and what we want to look for in our sampling distributions. Small spread, centered about the parameter, and with a nice shape that doesn't start pulling on our calculations very much. Okay? And that's it for section 7.1. We'll stop there. Homework in the text that I'll send out. And you can work on that. We'll have some time in class on Monday to work on that as well. And we'll start working towards a quiz probably on Tuesday. All right? Have a good weekend. See you guys on Monday.